Hello. It seemed like some time ago I had this problem, and the problem was to find take 2 point charges, find out where the electric field was zero. That's actually a pretty easy problem. And then the next question was, where is electric potential equal to zero? Well, if you want to find where the potential is equal to zero along an axis connecting the 2 points, that's pretty easy too. But what about in 2 dimensions or even 3 dimensions? 3 dimensions, I didn't even think about that. Okay, so let me just show you the program I wrote, and then I'll show you how I'm going to do this. So let's switch over to here. So this is the program that I created to calculate and solve for the location where the potential is zero. So here I have 2 point charges, a positive one at the origin and a negative one right there, and this blue line represents the location of where the total potential is zero in the xy plane. But mathematically, it's not the most trivial thing to solve, and so I want to come up with another way to do it. So let me switch back to paper because I'm going to change this program or just rebuild the whole thing. Let's see. Okay, so let's talk about potential. So if I have 2 point charges, and I want to find the potential at some particular location, the electric potential with respect to infinity is a scalar quantity. And so if I just take the potential with respect to infinity due to 1 point plus the potential with respect to infinity due to the other point, then I can find the total potential right there. Now, if I want to set that equal to zero, it's not trivial to solve this problem because here I have R1, which depends on, this vector, which has an x and a y component, and that has an x and y component. So you have really four. Well, you actually you want this x and y, right? That point has an x and y, and these vectors are in terms of that x and y value. So I have two variables in there. So it's not super trivial to solve. You can do it in one dimension where you say y is equal to zero. That's pretty easy. So what if there's, and there's lots of ways to solve equal potential lines, but I want to do something fun. I like fun stuff. Okay, suppose I have this in one dimension. Suppose I have the Vx as a function of x. It's some potential. And the potential looks like this. I'm just making up something here. Okay, so it's some curve. And I want to find out where this is, where that point is right there. So first of all, I know that there's a relationship between the electric potential and the electric field, right? So the electric field in the x direction is equal to negative, I can write it as delta V. That's not the x, that's the total potential. Delta V over delta x. It's the rate of the rate of change of the electric potential. So what's important about the electric potential at this point? Well, nothing, right? Because if, let's say I have a positive charge and I put it right here, then the force is going to be pushed, since the slope is negative, the force is going to be positive. It's going to push this charge essentially down this hill, right? So it's like rolling a ball down a hill. And if I get to this location, what happens? It's going to get to that location, but it's not going to stop. It's going to keep on going down, right? So the force is not zero there. Just the potential is. So, the idea was if I take my 2 point charges, it's not a dipole, and I have a test mass over here, so these don't move. These are fixed in place. I can calculate the net force on this. It'd be something like this. F equals QE, where this is some test charge right there. And if I do that, I can make this thing move around these two charges. And it's going to go not necessarily to lower potential. Well, kind of. But it won't stop there. Okay? So it may move something like this. I don't know. But what if I look at that in one dimension and that charge would move down here and keep going? Now and I let it do that. But now I say, okay, I'm going to change my potential arbitrarily. I'm going to say, I'm going to flip this up like that. So if the potential is negative, if V is negative, then I'm going to take the inverse of the force. So I'm going to flip the force. So down here, I'm going to say EX equals negative delta V over delta X. Here I'm going to say EX equals delta V over delta X. So in this case, this ball would come down here, and then it would go up and then back. And so it would oscillate back and forth around that thing. And if I give some drag force, so if I say F drag equals negative K times the momentum, then that would make it actually slow down and eventually get down to here at a point of zero potential. So here's what I'm going to do. I'm going to start with, and I think this will work. Okay, I'm going to start with the point right here, and I'm just going to shoot it. And if the potential is less than 0, I'm going to flip the force. Okay, and then I add a drag force, and hopefully this thing will come down and like settle somewhere, maybe right there, and that will be a 0 potential. And then I can take another one and shoot it at a different angle, and I can keep doing that. I don't know how this is going to work, but it might be fun. So let's do that. So let's just go back over here to our code. Our code. This is our code, right? Oh, that's not what I want. Computer view. There we go. This is our code, and we're going to make it work. I'm kind of excited. I like building things from scratch. Let's just do, I don't even know what that C stuff is. I wrote this a while ago. Let's just copy this whole thing. Because I want to make, in this case, I did some point charges, but I never visually displayed them. I want to visually do this in 3D. Okay, so I have K, there's Q1, there's Q2. S is the distance between them. I think that's all I need. Let's just make these two charges. So actually, let's do it this way. Q1 equals sphere. That one was at the origin, I think. Position equals vector 0, 0, 0. Radius equals, so S is 0.1, so it's 10 centimeters between them. So let's say a radius of, oh gosh, it's hard. Let's just say 0.01. Color equals color dot, I'll have them red and cyan. So the positive one is red. And then I'm going to say Q equals, this is the nice thing about Python, is that if I have a sphere object, Q1, I can give it a charge property called Q. And so I don't have to have a separate variable. So now let's put down here, Q2 is going to be equal to a sphere. Position equals vector, it's on the x-axis, it's going to be equal to S, 0, 0. And I need to move this S up here. And I'm going to give it the same radius, 0.01. What color is it? It's color dot, so it's red, and let's do red and cyan. I would do blue, but for negative, but it doesn't show up as well. And then Q equals, let's see. Okay, so there I have my two charges. I'm going to stop there. I don't want to do all this graph stuff. Just get rid of all that. And let's run it. Save it. And yes, I'm going to give you the code. You know I'm going to give you the code. There's my two charges. Yay. Okay. So now let's make our test charge. Let's just call it T charge. TQ. TQ equals a sphere. Let's just put it somewhere. Position equals vector. Let's say on the x-axis, let's say it's 2 times S. On the y-axis, it's S. I'm just making some numbers. It should be smaller than those two, right? Because it's a test. It doesn't really have to be. So let's pay 0, 0, 4. And let's leave it as white. And let's say Q equals 1. It doesn't really matter what the charge is. Let's say Q equals, actually it does matter. Let's say Q equals 0.5 times 10 to the negative 9th. Yeah, this is going to matter when I get to the mass. So that actually is important here. Those two other charges, oh, you can't even see those. Turn off the camera. No one wants to see me anyway. There's my two charges. Those two charges are fixed in place. I'm not going to move them. So it actually doesn't matter where they are. and what their masses are and what their velocities are, they're all 0. So but this one does matter. So let's give this one a mass of tq dot m. It does matter what this is. Let's say it's super low massive because the force is going to be small. Let's say 0.01. I don't even know if that's going to work. I think it might work. And now I need the momentum. So let's say tq dot p, mind your q's and p's, is going to be tq dot m times the vector. Let's just shoot it in the negative x direction. So let's say vector negative 0.300, and we can change this stuff later. Okay, and I'm not going to add drag force. I just want to make this move first. So there's my charge. It's moving this way, and let's just see what happens. Okay, so I'm gonna say t equals 0. Oops. T equals 0. dt equals 0.01. And let's run it for 4 seconds. So while t is less than 4. Rate 100. That just says don't do more than 100 calculations per second in real time. We may want to change that later. Now the next thing I can do is calculate E. I want to calculate the electric field. So the first thing I can do is calculate R1. That's the vector from charge 1 to the test charge. So it's going to be tq.pos minus q1.pos. R2 is going to be equal to tq.pos minus q2.pos, right? tq.pos is the vector location of that charge. So now I have R1 and R2. Those are vector values. I need those to find the electric field. I think I can find the electric field. Let's just say E equals K, which I have up there, times Q1.Q, that's the charge of Q1, times norm R1. Norm is a unit vector R hat in the direction of R1, divided by the magnitude of R1. Mag is a built-in function that returns the magnitude of a vector squared. Now I just need to do the same thing for charge Q2. So I'll say plus K times Q2.Q, which is negative, times norm R2 divided by mag R2 squared. Now I can calculate the force. It's just going to be equal to tq.q times E. And now I'm going to use that to update the momentum. So tq.p equals tq.p plus F times dt. So this is the Euler method of calculations. I am going to use that force over a short time interval, assuming that it's constant, which it totally is not, and use that to update the momentum, since F net equals delta P over delta T. Now I can assume the momentum's constant and use that to update the position. So I'll say tq.pos is tq.pos plus tq.p times dt divided by tq.m. So up here, I need to do this too. Make trail equals true. Let's save this. I think that, I need to update time. So now I need to update time. T equals t plus dt. Let's run it. Nothing. I guess the force is, the mass is maybe mass is too big. It did bend. Okay, so let's make it, it's doing stuff. Okay, so that was 1, let's say 1 times 10 to the negative 6. There we go. Okay. Huh. I think that's right. That's pretty cool. Okay, let's make that a little bit, let's make that even smaller just to see what happens. Okay, so it went through that one. That was bad. Let's make it 7, 3. Let's see what happens here. It still goes through. Okay, I think that's okay. No, I know I want to make it. Let's make it a little bit bigger. No, let's do 7 times 10 to the negative 7. Okay, that's pretty good. Okay, now let's see if we can do this idea. Let's calculate the potential. So now I'm going to calculate the total potential. V equals K times Q1.Q divided by mag of R1 plus K times Q2 dot Q divided by mag of R2. That's the potential. Now I can say if V is less than 0, then F equals negative TQ dot Q times E. And if it's not, then it goes to its normal equation. I think that might work. Let's just try it. Did it change? You know, I might not have gone through a potential. Let's move, that's one thing. Let's move this up a little bit. 2 times. If it never, oh, it should cross one on the other side though. Yeah, see, it's not getting a potential right there. Okay, so let's put this back, and let's put this at 3. It should definitely cross a potential in that case. No? If V is less than 0, let's do this. If V is less than 0, TQ dot color equals color dot yellow. So it changes colors if it crosses. Yeah, see, that's not doing, it never changed colors. That's weird. If V is less than 0, if V is less than, I just calculated V, K, Q1 over the magnitude, K, Q2. It's like it's never 0. Okay, let's do this. Let me go back to my code. Oh gosh, I gotta find it now. Because what I want to do is look at where I calculated that potential of 0 is. Rotating potential plot, equivalent 1D, 0 potential plot. Let's see if that's it. Yeah, okay. So just looking right here, that's a distance of 0.1. That's a distance of x equals 0.13, y equals, so it's very close, right? It's very close. I actually need to get this closer. I think it's going too fast. That's what I think. So let's say this is 0. Let's just put that at 0. I'm looking for a color change. It changed. But it didn't turn, it doesn't seem like it turned around. Maybe it was just going too fast. Maybe that was it. So let's say I put this at, I know the potential was at, let's just add a drag force. So let's just call this C equals 1. Let's just try that. So now if, let's just add in here plus C times TQ dot P minus. And then this one's going to be minus. Oh, I see what I did. I see what I did wrong. I see what I did wrong. Even if I get that, if I put this up here, it should work. Because what I did was, if it's less than 0, then I had the calculation right there to change it right back to what it was. That was my problem. Let's see, look for the color change. There, see? Now it should come back. Okay, I need to run it for a longer time. Let's run this at faster and run it for longer. See, look at that. Okay. So it looks like it's oscillating around these zero potentials. Now I just need to put that drag force in there and we should be good. So let's say minus c times tq dot p, and then this one will be minus c times tq dot p. Let's see what happens there. That drag force may be too high. No. Check that out. Okay, let's do... I want to turn on the trail. Let's not turn... I want to only turn on the trail once it gets to zero potential. Okay, let's do that. Let's say... if... not actually at zero potential. So if V is less than 0.01, so it's close, then tq dot make trail equals true. And then up here I'll just put tq dot make trail equals false. So it only gets turned on when that is less than that value. And I should do plus or minus. So let's say, how do you do absolute value? ABS, is that right? Okay, so it's only going to make a trail when it gets down to, no? Maybe it needs to be much more than that. But that's pretty cool. I don't actually need the trail. Let's leave that alone. Okay, so, now let's try adding some more masses. Okay, so how am I going to do that? I could just repeat this whole thing. What I really should do is make it a function. How do I do that? How to make multiple things? Make a function. Let's call it, let's do that. Def shoot thing. Let's call it shoot. And I want to give it, I want to pass into it a location, R, S for start, and a velocity, a momentum, P, start. And then once I do that, I want to make a point. I'm just trying to think, that might be too many, and the initial position will be equal to RS. And the mass, and that's all fine. I do want to make it a little bit smaller. Now I'll leave it that way. The charge is fine. The mass is fine. The momentum is going to be equal to, actually let's do this as VS. I had that as VS. VS. So there's my momentum. Now my drag force, my T, my DT, my while loop. This does, I want to make that even faster because I'm not going to, who's going to wait around for a bunch of things, right? Indent all this. I don't think that make trade thing is working. Indent this. Okay, and that will, I could do this for as long as it's still moving. How about that? So let's say while tq.p, while the magnitude of tq.p is greater than the tq.m, the mass, times the velocity, times the initial velocity. I wonder if I could do that. Well, let's just say 0.001. Yeah. Okay, and then I could return the position. I guess I should do that. Let's say return tq.pos if I want to do something with that. Okay, now let's try running that. So let's say shoot. The ball was at vector S0 with the velocity of vector negative 0.100. Now, and I do have a problem in here. Let's just see what happens. So, Okay, that's pretty cool. Now, so the shoot seems to work. So now let's say, let's count, let's do this. I'm having fun. I don't know about you, but I'm having fun. Okay, so N equals 50. I'm going to shoot 50 balls. N equals 0. So I'm going to count up to 50. So I'm going to say, while N less than N, do the following. Shoot a ball. Now, I don't want to just shoot a ball, right? Because I want to shoot different balls. So let's shoot them all from the same let's just put them in random places and shoot them. That'll be fun. Okay, so the vector location is going to be equal to a maximum. What do I want my maximum S value to be? I want my maximum position to be. Let's see, from let's say 3s to negative 3s. So I'm going to say 3s, 3 times s. Oh, that's actually, I have to do 6 times 1 minus 2 times random. So 1 minus 2 times random is going to give me a number between -1 and 1. So actually this should be 3. And let's put the same thing for just the x-axis, or the y-axis. And then for the velocity, I want to go again from, I want them to all, I don't know, let's just do, I'm going to have to put something in here. I just realized that. So let's just do a velocity of -0.2 times 1 minus 2 times, oh no, positive, it doesn't really matter though, times 1 times 2 times random. And let's put the same thing for the y coordinate. And we can change this to z also in just a second. Why is this not? What's wrong? I think I don't have enough spaces. Okay. So 2 times random, that one's going to be the same thing. And now, ooh, parentheses. Okay, so now and then I need to increase N. N equals N plus 1. Okay, now up here, I could get in a position where it's like shooting away from the thing. So let's say while this is that, and mag of tq.pos is less than, I don't want to get too far away, let's say 5 times s. Let's see if that works. This might not work. Save it. Run it. Okay, that's too far away. Let's change this to 3s. 3s. Oh, there, I got one to stay. Another one. And you'll notice they turn yellow. See, these are just getting too far away. They're all getting the same spot. There's another one right there. Is that another one? I think so. Let's have them all shot somewhat towards the origin, right? Because I'm getting this, like, weird thing over here. That's weird that some of these get really far away. I guess they must be going super fast. Okay, so in my random velocities, let's do this. R temp equals, this is the location, it's going to be this. That's my vector location, and then this is to be R temp. Now, for the velocity, I want it to be somehow related to that. I guess I could do an angle and let's just run more. Let's see what happens. 1,000, and let's put this at 500. That might be a mistake. I feel like, oh, see these, yeah, it's starting to fill in. It's weird that they're all ending up over here. Oh, that's good. I'm going to declare this victory. Yeah. Okay, I'm going to play with this some more and see if I can make the code better. But I think it's a good idea of finding this, right? Actually, I'm going to change one thing. I'm going to make it in 3 dimensions right now. But I can also change one of the two charges to the same sign, so there'd be a dipole, and I know where the equipotential line would be a straight line in between them. What am I thinking about right now? I think this is kind of cool. It should be in 3 dimensions. Now, what if I want to find a 1 volt potential line? I just do the same thing, right? I could do the exact same code. All I do is change this if the absolute of V is less than 1 volt, then it switches directions, right? And maybe I'll do that now. I don't know why these things are getting so far away right here. That's kind of weird. I guess they're just going super fast. And by the time they're going so fast by the time they get there. And why am I not getting any, I guess over here, it's really hard to get them to stop because the forces are very large. That might be it. But maybe we could randomly get one there after a while. So let's do this. Let's do this in 3 dimensions. So I'm just going to go over here and I'm going to copy this. I'm going to put it right there. And let's see what happens. So now the numbers, the points are generated in 3 dimensions. See? Although it looks pretty flat. And these should end up in a sphere, right? There should be a sphere around these two that is equal of 0 potential. And I don't know why those are yellow. Actually, I do know. If it's less than that, I make it yellow. But once it goes below that, it stays yellow, right? It never goes back. So let me go up here and say tq.color equals color.white. Is that correct? Yeah, that might work. Okay, I'm happy enough with this that I'm going to stop. I'm going to give you the code to this. I'm going to give you the link to the other programs. I'm pretty excited. This is really fun. I mean, it's not the best way to do this. It's a fun way to do it, right? Physics is about playing around and just having fun with stuff, and I'm definitely having fun with this. So hopefully you can find the code, play with it too, do some cool stuff, make something cool. Something's not right because it's not. It should be as many points over here. But maybe they're there, but they just collapse down. I think that's what it is. They collapse down to this 2-dimensional plane. No, there's one over there. Okay. Let me just double check. I may have copied it wrong. Our temp is, aha, that's why. I didn't put 3. Oops, I missed it. I did that wrong. Okay, so now it looks like it's in 3 dimensions better. It was doing 1s. And so what I should do is, if it's too far away, just make the size of the thing small. Let's do that. Let's say tq dot radius equals 0.00001. Otherwise, I'm going to make it 0.004. So only when v is less than that. Up here. Let's see if it... I don't know why that didn't work. tq.radius equals 0.004. Let's run that, see what happens. Okay, so now no, I'm not sure again. I think it's just ending up and they're too far away. Or the potential... Aha! The potential gets really far away. If you get really far away, it gets small. So, Okay, that was a bad idea. But again, I'm going to stop. I said I was going to stop. I'm really going to stop this time. I hope you enjoy this. Again, I'll give you the link down below, and I'll talk to you later.